Let me start with the solid state, the session 3rd class. If you do remember, whatever we have taken different types of solids, crystalline, amorphous solids last week, and simple arrangements, and then calculating the effective number of lattice points and FCC body centered and simple cubes. Let's see with the next part of it. Just a minute. I'm sorry. I've taken the third one instead of the fourth one, which we have done. Okay. Let's take about the hexagonal closed packs lattice arrangement. A little difference from what we have done it. See, these are the corner ones. These are the corner lattice point. This would be the face center. And this again would be the face center. And what is this? Hexagonal close packing. Top and bottom hexagonal faces will have 6. See, you can see 3 here, 6 of them at the corners surrounding a central atom, which will be the face center. Inside, in between, you will have 3 of the lattice points. Something more or like, it's like a body centered lattice points, which is not shared by any other unit cell. So at the corners, if you consider this as one layer, this is another layer, and the same type of layer you will find it over here. Yes, the top and the bottom will be of same layers. In between, you will have a different layer. In the in-between layer, you will have 3 lattice points, which will not be shared by any other unit cell. And here we have how many? 6, and 1 at the face center, and 3, let me say, they are the center of the body. Fine. Okay. Contribution of atoms at the corner. If we take up a cubic unit cell, there were 8 shared by 8 other unit cell. But here we have 6 at the top, 6 at the bottom, a total of 12. But they are shared by 6 other unit cells. So the contribution will be 12 into 1 by 6. It will be equal to 2. And face centers, there were 2. And the contribution is 2 into half. Will be equal to 1, and all the 3 will have the contributions as such. So 3 are there as such. So what is the contribution of this? It is 1 by 6. This will be a contribution of 1 by 2. These will not be shared by any other unit cell, so it will be equal to 1. Hope it's clear. The way na enna solren. Here it's 1 by 6. When we go for a simple cube, it will be 1/8. Here it's only 1/6. This is the packing efficiency. What do we get? We get the void space. Void space is equal to 100 minus the packing efficiency. So we have seen how the atoms or the constituent particles form the different lattice types. And what do we mean by the coordination number? So if I take sodium chloride, or let me take an iodine solid as an example, 2 different examples I am taking. The number of nearest opposite neighbors, that is number of chloride ions which surround the sodium ions, or the number of sodium ions surrounding the chloride ions, will give us what is called as a coordination number. Whenever we are talking about an ionic compound, the coordination number is number of nearest opposite, let me write, opposite neighbors. And for molecules or elements, we don't use this word opposite. We'll only just say number of nearest neighbors, the coordination number. So we will see all these in the next part of it. How do we calculate the coordination number? How do we check the voids and then the packing efficiency? I mean the relation between all those things. Let's continue. Yeah, the number of nearest neighbors of a particle is called as the coordination number. Coordination number will be linked to the packing efficiency, which we are going to see. Like in ionic compound, like let me say if it is FCC, the coordination number will be different. The HCP, the coordination number might be different. Body center, the coordination number will be different. It depends on the packing efficiency. Coordination number will be linked to the packing efficiency. Which are the ones which are packed efficiently are the HCP and the FCC. Next efficiently packed of whatever we have seen is BCC. The least is simple Q. These two have same packing efficiency of almost 74%. Okay, let's see how we can make up a three-dimensional structure from a one-dimensional structure. Here all the ions, atoms or molecules as solid sphere. Let's take a one-dimensional closed packing. We'll try to arrange all the lattice points one beside the other. And this is one way of arrangement of the lattice points. We are trying to put the solid spheres together in one single line. That will be one-dimensional closed packing. When it will have a nearer, if I take a middle one, not the other one, it will always have a coordination number. 2 will be the nearest neighbors. The one in the middle will have one neighbor on either side. The coordination number is 2. Fine. The one in the middle will have 2 neighbors. Then in a 2-dimension, that is once we place one below the other. I mean, this is one way of arrangement. If I take this one, we are exactly placing one below the other. Can you see that? We are stacking them one below the other sphere. We are trying to put one below the other. Here we are stacking them equally on the same side and exactly ஒரு sphere க்கு கீழ இன்னொரு sphere வெச்சா we get what we call it as AA type of stacking. If I take AA type of stacking, take anything in the middle, it will have, and if I want to look at this, how many are the nearest neighbors are 4. We call such a close packing as square close packing. And I am drawing a square here. So we call it as a square close packing. Now the other way of arrangement is, instead of putting one below the other, try to put them in between the spheres. If you put one second layer in between the spaces of the first layer, we get what we call it as AB type of arrangement. This is an arrangement, AA type of arrangement. If I take A in the sense, same type of arrangement. If it is AA type of arrangement, the coordination number will be 4. Now if you take anything in between, let me consider this in between. Yes, I can. Hexagonal close packing. Hexagon vardilla. So we call it as hexagonal close packing. How many are surrounding this? 1, 2, 3, 4, 5, 6. Hexagonal close packing la coordination number on the 6. Other square close packing at the 4. Other single one dimensional at the number the coordination number is 2. என்ன ஏதாவது டவுட் இருக்கா? Shall I continue? இது வந்து ஸ்கொயர் க்ளோஸ் பேக்கிங். ஒரு லேயருக்கு கீழே இன்னொரு லேயர். ஹெக்ஸாகனல் க்ளோஸ் பேக்கிங் என்ன பண்ணுவோம்? ஒரு லேயர் நடுவுல இன்னொரு லேயர், ஐ மீன் ஏதாவது என்ன ஸ்பேஸ் இருக்கு அந்த ஸ்பேஸ்ல இருந்து நம்ம ஸ்டார்ட் பண்ணோம். இங்க நம்ம என்ன பண்றோம்? ஃபர்ஸ்ட் லேயர் நடுவுல ஏதாவது ஸ்பேஸ் இருக்கு, அங்க இருந்து நம்ம நெக்ஸ்ட் லேயர் வந்து ஸ்டார்ட் பண்றோம். இது வந்து ஹெக்ஸாகனல் க்ளோஸ் பேக். என்ன டைப்னு சொல்லலாம்? ஏபி ஏபி டைப். ஏன்னா இது ஒரு டிஃப்ரெண்ட் லேயர், இது வந்து ஒரு டிஃப்ரெண்ட் லேயர். சேம் லேயர் வந்து நம்ம we are getting it again ஏபி ஏபி டைப். ஓகே, நம்ம வந்து ஒரு டைமென்ஷன்ல பார்த்தா இப்ப 2 டைமென்ஷன்ல எடுக்கலாம். Fine, the same thing stacking arranged in a 2-dimensional square packing. We are trying to make a simple cube from this. 2-dimensional and we are going to a 3-dimensional square packing. இது வந்து என்னது? நம்ம ஸ்கொயர் பேக்கிங்ல இருந்து போறோம். We are going from a 2-dimensional square packing to 3-dimensional, going in a 3-dimensional way. What are we getting is a simple cube. So can you see the square packing here? நம்ம 3-dimensional எடுத்தா நம்மளுக்கு கோஆர்டினேஷன் நம்பர் எவ்வளவு வருது? 6 வருது. You can see one at the corner, the others at the corners and everything. You can see 6. So if I take a 3-dimensional square packing, the coordination number will be 6. What does that mean? The number of nearest neighbors in simple cube is equal to 6. Can you see that, ma? Are you able to visualize how we are getting 6? So let's go on. When here it's clearly shown how we are getting as 6. How we are trying to put from 2-dimensional square packing a 3-dimensional BCC structure. So what are we trying to put in between the spaces? When this blue color is one layer, in between the spaces we are trying to put another layer called as B. Fine, the broken line indicates the layer B. இந்த டிஃபரன்ஸ் வந்து உங்களுக்கு தெரியுதா? இது வந்து A, இது வந்து B, 2 different layers. இங்க அத காட்டிருக்காங்க. இது வந்து கார்னர், இது என்னமா? பாடி சென்டர்ட். lattice point. So we have already seen this in the last class without the coordination number. நம்ம வந்து arrangement பார்த்திருக்கோம். How the corners are making up one effective lattice point and how the middle one is making a 1. You can clearly see that these 8, I mean they're very close by if you can see, but what we are trying to do is move them far apart from each other and then make What is that? A cube structure. You can clearly see over here how we are getting it as a cube. Hope you can visualize this one clearly. Coordination number வந்து 8. எப்படி 8 ஆகும்? இதுக்கு I mean the one whichever is the body centered has 8 nearest corner lattice point. To the center one, for the center lattice point, there are 8 corner lattice points. So in the 8 number, if you take up another one, the same thing will happen, that even every corner, if you take complete 3-dimensional structure, you can also feel that every corner is surrounded by every corner. Every corner is also surrounded by body center. MDL, sorry. Are you able to understand how we are getting a coordination number of 8 in a body centered crystal lattice? Taking up a 3-dimensional structure. We went from a square packing to a 3-dimensional structure. Slowly we are trying to show what is the exact coordination number in a 3-dimensional structure. Shall I proceed? Fine. So let's go to the hexagonal flow span, where initially itself what did we place? We made it as AB type, right? First we made A and then B, AB type of arrangement. When we did a simple arrangement. Now we are trying to place another a layer over the first one. Placing second layer over the first one, if you see, we are getting T here represents a tetrahedral void, O represents an octahedral void. Tetrahedral void, how do we say? When it is, the space is surrounded by 4 lattice points, we get what is called as a tetrahedral void. If the space is surrounded by 6 lattice points, where do I take? I'll just take a different color so that I can show you that. Fine. Let me take something over here, the octahedral void. 1, 2, 3 are the dark ones that I have taken circles, and the lighter color ones are 1. This is the lighter color and this is the lighter color. There are 6 spheres which will surround that small space. 3 in this way, triangle madri. In the space mela I have to put 3 more so that it makes an octahedral void. Tetrahedral we will get only 4. Only 4 spheres. If I put one more at the top of this space that is covered will be a tetrahedral void. So we get 2 tetrahedral voids surrounded by 4 lattice points, octahedral void surrounded by 6 lattice points. Fine. I showed the same thing. 6, 4 is when 3 are there and 1 at the top. This void that is formed as a tetrahedral void. It's a tetrahedron shape. Fine, understood? Can I proceed? Fine, octahedral one, see, there are 2 different colors, 3 in one layer. At the top we have 3 more layers. We are getting with 6 and octahedral. You can see it's almost like when I put a triangle like this. 3 in that form and 3 in this. The space that we get is see, the same thing is shown here, an octahedron. Though it is 6, we call it as an octahedron because the number of faces, the lines, plane that we take, we'll get 8 planes. We call it as an octahedron. So we have tetrahedral voids and octahedral voids that are formed by the showing of a hexagonal closed pack structure. Are you able to understand? Shall I continue? Okay, if I take the number of tetrahedral and octahedral voids in any particular closed pack structures, if the number of closed pack structures that we get in a particular crystal lattice is equal to n, the number of tetrahedral voids that we get would be equal to the double the number of closed pack structures that we get, and octahedral voids will be equal to n. The closed pack structures will be equal to the number of octahedral voids, while tetrahedral voids will be equal to the double the number of the closed pack structures. Remember this, in case if you are taking it as an FCC, we got an effective number of atoms as 4. So tetrahedral voids will be equal to 8. Octahedral voids will be equal to 4. In HCP we have seen Z effective was 6. Tetrahedral voids will become 12. Octahedral voids will be equal to 6. So in general, instead of putting either FCC or HCP, we can directly put this one, the number of closed pack structures. In case if you don't understand whether it's an FCC or a HCP, this will be the basic one. CCP is to tetrahedral voids is to octahedral voids. You can take it as 1 is to 2 is to 1. One very basic problems will be asked based on it, and it's easy to answer them. My doubt irka, shall I continue? I'll continue. Fine. Let's see the animation on this. First the tetrahedral void, then an octahedral. HCP structure, hexagon 6. Can you understand how it has been arranged? Can let's go the next one. Fine. You can see the difference now. Hexagonal and cubic. Just see. It started with the first layer, then you can see the building up of layers. You can see it again. Now this layer is formed. In hexagonal close packing, what are we getting? AB type. In cubic close packing, you can see a difference of ABC type. Shall I again show you the animation, or you are able to understand it? So the coordination number in the CCP and the HCP structure will be equal to 12. Fine. Let's see this. In a compound, atoms of element Y form closed pack structure, that is Y is forming the CCP. And those of elements X form 2/3 the tetrahedral voice. What is the ratio of closed pack structures to tetrahedral voice? Is 1:2. Take in this way. So Y is 1 out of 2, 2/3 is only substituted. So let me put this as, where do I put? Y, X, this is 1, this is tetrahedral voice is twice that of the closed pack structures. But how many tetrahedral? Not all tetrahedral, only 2/3 is occupied. It will become 4/3. I cannot write the formula in ratio. So what do? I want to make it a formula. 1:4/3. I'll multiply throughout with 3 so that we don't get any fraction. So multiply this with 3. It will become Y3X4. So X4 Y3. I wrote it in Y and X. Here the options are given with X and 4. Sorry, X and Y. Are you able to understand how we are getting this? Sorry. X4 Y3 is the answer. Understood how we are getting this? X4 Y3? See, CCP structures and the tetrahedral. This is forming a CCP, this is forming a tetrahedral void. Initially, if you remember, I said the number of, consider this as 1, the number of tetrahedral voids will be 2. But how many tetrahedral voids are occupied? Only 2/3 of it is occupied. It's equal to 4/3:1. Since I cannot take the formula in this term, what I will do is multiply throughout by 3 so that I can cancel. It's 4/3 into 3 is to 1 into 3. So it will become 4, Y will become 3. So 4:3, X4, Y3. Are you able to understand this? Good, very good. Fine. The same way, just try doing it. A compound is formed by cation C and anion A. These form HCP structures and these form octahedral voids. What will be the ratio of it? 1:1. But only 75% of octahedral voids are filled up. So if I take octahedral voids, 1 into 3/4:1. Why 3/4? Because it's given us 75%. Again, what should I do? I cannot take the fraction. I will multiply throughout with 4. sorry, C and then A. So it become 3:4. C3, A4. Are you able to get the answer as C3, A4? Any doubt? Any doubt how you are getting this answer? Is it fine? Shall I continue? Fine. First you try doing it, then I will do it. A mixed oxide is cubic close pack. Oxide ions a divalent metal ion and a monovalent metal ion is forming. This is octahedral, this is tetrahedral. And these form the close pack structures. Yeah, that's what I wrote it. Oxide ions are forming the close pack structures. First, let's take the ratio 1:2:1. And what's given? 1/4 of tetrahedral voids are occupied. One is to 2 into 1/4:1. They didn't say anything about how much of octahedral voids are filled up, so it means all the octahedral voids are filled. So 2 goes 2 times, so it is 1:1/2:1. As I said, we cannot take the fraction, so what we will do is multiply throughout with 2, we get 2:1:2. So A is 1, B is 2, O is 2. Did you get this answer or did you get anything different? Is the answer same for you also or you all? Should I repeat it or are you able to understand it? Fine, we got AB2O2. Fine. As the coordination number is increasing, the packing efficiency also increases. What is SCC? Simple full cube. It's 6. And what did we calculated yesterday? 52.5% is efficiency. Void space was 100 minus 52.4. Here void space was 100 minus 68. Here is 100 minus 74. BCC is body centered. The coordination number is 8. FCC, face centered or the hexagonal close pack, we are getting a coordination number of 12 and the percentage efficiency is 74. So as the coordination number is increasing, the packing efficiency is also equally increasing. Fine. Let's see what type of arrangement. So this is the part of the periodic table taken and see how the different types of crystal lattice these metals have. We are talking about metals. We didn't go for the ionic compounds anything. We are first doing with the metals. So these are your S block elements. Your 1A group elements are the first group. This is your second A group element. This is third A. And from here till here is your D block elements. Because we are talking about metals, we didn't go with the P block elements. So you can see a square with a blue color, but whatever the simple notation that has been given as body center, and lighter blue color is face centered. You can see there is only one with a simple cube and many were with hexagonal BCC or the FCC. See, all alkali metals will have a body centered cubic crystalline structure, and if you go with the second A group elements, beryllium and magnesium are having a hexagonal flow span. It's only a comparison for you to study. Sometimes it so happens in the D and the F block elements, the transition metals that you have in inorganic part, there you have the clear comment about the D block elements, especially where they have given us the different types of crystal structure. Let's just give a reading so that you understand it. Calcium and strontium, if you see, they are FCC. Again, barium is a body centered one. Aluminium is again FCC. Manganese is the only one which has a simple cubic. Again, all these are your FCC. You also call them as transitional triads: cobalt, nickel, copper, ruthenium, palladium, silver, and all. Transitional triads, or you can also call them as the coinage metals: copper, silver, and gold. All these things. Zinc, cadmium, down you get mercury, which is the liquid form, so they didn't go over the part. So the rest of the things. Any doubts so far? Okay, on heating, iron changes its lattice arrangement from BCC to FCC. BCC was the coordination number, and what's the coordination number for FCC? As the packing efficiency increases, the coordination number will also increase. BCC coordination number is 8. FCC coordination number is 12. Simple cube, the coordination number is 6. So as the coordination number is increasing, the efficiency is also increasing. What will happen to the coordination number is increasing? Effective number of atoms, here what did we get for BCC? 8 into 1 by 8 plus 1. Here for FCC we got 8 into 1 by 8 plus 6 into 1 by 2. How was it for HCP? 12 at the corners into 1 by 6, 2 at the face centers into 1 by 2, shade by 2, and 3 at the center of the body. So it is 2 plus 1 plus 3, 6. Effective number of atoms. I am not talking about the coordination, effective. So if it is FCC or HCP, coordination number will be 12. But look at a slight variation in the effective number of atoms. In FCC we are getting it as 4. In HCP we are getting it as 6. So on heating, iron changes its lattice arrangement from BCC to FCC. What will happen to the coordination number? Coordination number is increasing and effective number of atoms per unit cell as a result will also increase. Coordination number changes from 8 to 12. Effective number of atoms changes from 2 to 4. Right? Got that? Fine. How do we locate the tetrahedral and the octahedral voids? So, complete crystal lattice is what has been represented here. So, divide that into 8 parts. one void inside each part, so there will be 8 tetrahedral voids. See, these 4 are making up a space in between. This is a tetrahedron that is formed. From here to here you can see all these together are making up a tetrahedron. The same thing we can make up many such parts, taking up the complete crystal lattice divided into 8 equal parts. We get 8 tetrahedral voids. But if I take up the complete closed pack structures, we'll get only 4. Where do we have the octahedral and the tetrahedral voids? So at the body centered, we have what is called as octahedral void. And at the edge center, what do we mean by edge center? This is the edge center. So at this position and this position, we have what is called as an octahedral void. At the edge centers and the body center, we have the octahedral void. So one at the body center of the cube and at the edge. Any doubts so far? Tell me anything that you want me to repeat. I'll repeat it. Any slide, any explanation that you want me to do it? Did you understand how we got this coordination number and everything? Effective number of atoms. Any calculation you want me to repeat it? Maithili, edavadhu repeat pannuma? Any explanation that you want me to repeat, I'll repeat it. Coordination number 8 is for BCC. This is for FCC. It can also be a HCP. Z effective for BCC is 2. For FCC it is 4. How we are getting this as 2? 8 lattice points at the corners and 1 at the body center. For FCC, how we are getting? 8 at the corners plus at the face center. So how much are we getting? 1 plus 3, 4. Okay. Mixed oxide one, you want me to repeat it? I'll repeat it. Fine. Is it the mixed oxide? Fine. I'll do that. Fine. Let me take closed pack structures, tetrahedral voids, and octahedral voids. Remember the ratio is 1:2:1. That is, if there are n closed pack structures, the number of tetrahedral voids will be 2n and octahedral voids will be n. So they are the ratio of 1:2:1. And here it's given the closed pack structures are formed by the oxide ions. The cubic unit cell of mixed oxide is composed of oxide ions. So it means the closed pack structures are formed by the oxide ions. 1/4 of the tetrahedral voids are occupied by a divalent metal ion. So tetrahedral voids are made by a metal ion. Divalent is given. So metal ions will always form a cation. So it will be B+2. How much is it from? 1/4. So since the number of voids are double, it will be 2 into 1/4, because not all the tetrahedral voids are occupied. In the complete crystal lattice, only 1/4 of them are occupied. So let me take this. This is complete. Then, and a octahedral voids are occupied by a monovalent metal ion. So I'm writing it as A+. So all the octahedral voids are occupied because there is nothing given there. Either half full are occupied. So now what will be the ratio? 1:1/2:1. I cannot take a fraction in the formula. That you will take only for a non-stoichiometric compound unless the structure is defective. In all other cases, we write the formula with a whole number for every atom. So how do I do that? If you can recollect your empirical and molecular formulas, what we try to do is we always multiply with some number, the nearest number, so that all will become whole number. The smallest number that we can multiply is 2. So this will become 2, this will become 1, this will become 2. What is 2? Oxygen is 2, O is 2, divalent. Okay, I wrote for metal A is divalent, metal B is monovalent. A is +2, B is plus. So this will become A is 1, B is 2. Let's rearrange in the form of AB. So it will become A, B2, O2. Did you understand? Maithili, you asked me this problem only or some other problem? Where the problem with mama? Idu poduma. Should I repeat the other problems also? Did you understand? I'll repeat this also. Here it's given as HCP, whether it is HCP or CCP. Remember, number of closed CCP, we generalize it for FCC. Even if FCC is given or CCP, understand it as the CCP only. The number of CCP means closed cubic packed structure, so it will become FCC, face centered closed cubic. Number of closed packed structures are N. Tetrahedral voids will be double the number of closed packed. Octahedral voids will be equal to N. So let me repeat this. So HCP would be N. Tetrahedral voids are 2N. Octahedral voids is N. A compound is formed from cation C and an anion A. The anions form hexagonal closed packed. So anions are forming this. They didn't say about any charge, so I'm just writing it as A minus. Cations form. Cations, nothing about the tetrahedral voids are given, so let's not take this. The octahedral voids are occupied by the cations C. Only 75% of octahedral voids are filled. So out of 1, only 3/4, in case if it is 1, only 3/4 of it is occupied. So it is HCP is to octahedral voids is 1 into 3/4. So we'll get 1:3/4. 1:3/4 I cannot write, so I'm multiplying with 4. So it is 1 into 4 is to 3 by 4 into 4. So it will become 4:3. What is 4? Cation C is 4. Cations occupy octahedral voids. This is octahedral voids. This is anion E. So A4 C3 should be the formula. Then the formula is given with C3A4 because we generally write a cation first and anion next, C3A4. Understood? Fine, let's firstly go for this. A compound is formed from, only thing you will have to remember is the number of closed pack structures are n, tetrahedral voids is double the number of closed pack structure, octahedral voids are equal to the number of the closed pack structures. So CCP is formed by Y and element X occupies tetrahedral voids. First we will take the ratio that we have learnt, that is closed pack is to tetrahedral voids is 1:2. So first write what is known to you, then you write what is given. 2/3 of the tetrahedral voids are occupied. So 2 into 2 by 3. 2 into 2 by 3 is 4 by 3. So 1:4 by 3. Since we cannot take the fraction, we will multiply throughout with 3. Because I will cancel off the denominator in this way. So it will become y3 x4. x4 y3 would be the formula of it. So if it is clear, then we'll wind it up and then we'll see in the next class. Just give a reading of whatever you have it in your textbook. Fine, ma, shall I end up the class? Thank you, dear. Fine, thank you. Fine, take down the questions. If a compound is made up of atoms A and B, I'm making a little difference in the question. See if you can do. If A occupies the corners of the cube and B occupies all the face centers, what is the formula of the compound? Let me give you two questions, one on the mixed oxide. What is the formula of the compound? This is the first one. Let me do the second one. Matli, could you see the question? A compound is a mixed oxide oxide ions form the closed pack structures and divalent metal ion occupies half of tetrahedral voids. And monovalent divalent metal ion B and monovalent metal ion A occupies half octahedral void. What's the formula of the compound? Do these two questions. Thank you.